I just purchased a new Dell XPS 13, and I love the laptop. It does everything I want. Before this, I was using a MacBook Pro, and I realized my entire professional and educational career, I've really only been using Apple-based keyboards. That's not really a problem, but it turns out that almost every other vendor builds keyboards with a very particular difference. I really like when the function key is the lower leftmost key, but all the other vendors put the control key there. In my frustration, I decided I wanted to remap these two keys. Most operating systems have user applications, or native ways that you can tweak the keyboard map. For example, you can tweak the Windows registry if you have administrative privileges, or you could use a program like AutoHotkey. macOS gives you lots of mapping options and system preferences, or you could use some custom program like Carabiner. On my machine, I'm running Linux, and there's naturally a ton of options. Before we get too deep, let's just try to remap the function key as though it was any other key. Since I'm pretty stubborn and have lots of other things to focus on, I'm still running X11, and I'm going to use a very simple program and very outdated utility program called xmodmap, which modifies your keyboard under X11. This is like opening Carabiner or AutoHotkey and specifying the new mapping you want to use. You can see here that I've already altered some of the keys on my keyboard. I've swapped the Windows key, which is called Super in xmodmap, with the Alt key, bringing it slightly closer to the spacebar. The natural first thing to try is to remap the function key in exactly the same way. Looking at our xmodmap files, it seems that we need two pieces of information. First, the key code corresponding to the key on our keyboard, and second, the key symbol for that key. So how do we discover the key code and key symbol for any particular key? Well, there's a few ways to do it. We could write a simple program and capture the events, or we could use an existing program which might print all the contents of the X events to our screen. In this case, we're going to use a program called XEV. If you aren't familiar with X11, you can think of an X event as the same as all events processed by Windows 11 or Mac OS. Keyboard events, mouse events, whatever. When we open a new XEV instance, we can see that all the input events X11 handles are printed in a verbose manner to the screen. Keyboard input events, mouse events, and the like. So now we can see what the computer thinks is happening, capture those events, and then update our xmodmap file appropriately. You can see that when I press the letter A, some information pops up on the screen. There's a key press event when I press the keyboard letter, and a key release event when I released that letter. Each event has some information associated with it, including the key code and key symbol that we need. So we're pretty much done. When I hit a modifier key, the same thing happens. Information about the key is displayed to the screen. So, the moment of truth, when I press the function key, what happens? Unfortunately, absolutely nothing. It looks like our X server doesn't even see the event, even though I'm smashing the key on my keyboard. Interestingly, when I hold down the function key, I can see what look like completely new events being processed when I press other keys at the same time. We might be tempted to try to remap the entire keyboard in this one-to-one manner, but it looks like some parts of the keyboard are still dead, so that idea won't work. So our next step is to go and find the signal that the function key must be generating somehow. And to do this, it helps to have a basic high-level outline in our heads about how a computer sort of works. XEV and xmodmap are just applications. In the same way, League of Legends, GTA, Microsoft Word are all applications. Other applications are things like Bash, ls, cd, and all those other tiny little utilities you might use. These programs are all running on top of an operating system that actually lets you do things with your computer. The operating system itself is just a bundle of system-specific software that helps manage your computer hardware. It makes the machine usable and buildable for application developers. Things that might live in your operating system are the C standard library, systemd, X11, system call code, IPC, networking submodules, and the like. Finally, the operating system interacts with the actual hardware layer of your machine. The hardware includes basically everything that you can actually touch, like your keyboard, USB controller, CPU, SSD, GPU, Bluetooth chip, Wi-Fi, whatever. The software that runs on top of the hardware is generally divided into two different big chunks. The first chunk is all the stuff you can use and do as a user of your computer, administrative or otherwise, and we'll call this userland software. The second chunk is called the kernel, and it's effectively software that manages the critical physical systems that you have no access to as a user. This means things like the Wi-Fi chip, like your hard drive. The thinking behind this is that the kernel talks directly to the hardware. And as you, a user, should never really be able to interact with it, it keeps that separate from userland. The thinking here is that you don't want to accidentally touch the kernel, mess something up, and brick your computer forever. So whenever you do something on your computer, the data flow starts up here in the application layer, and then communicates only with the adjacent layer until it finally reaches the hardware layer. Since a computer is really just a big complicated device for moving electrons, everything is ultimately resolved to the hardware layer, and thus it passes through the kernel. There's one more piece to this puzzle, which we probably won't discuss too much, but we touched on it briefly before. Those Dell forum users seem to think we just needed to alter some settings or code in the BIOS. The BIOS is effectively a synonym for our last layer, UEFI, which is a layer sandwich between the kernel and the hardware. It helps specifically define how the hardware will interact with our kernel. Going back to our problem with XEV, we can now see that the application is running up in the top layer, which means it only sees the things the operating system passes along. Obviously, we can't remap the function key this way since no application is able to even see that the function key has been pressed. My next idea is to see whether we can go down into the kernel, capture the function key press event. And if we can, then we swap that event with the control key press event, and every application should just magically work, since in this case we've now mapped the information down in a lower layer. How do we actually do this? Well, we can write a kernel module, which we load at runtime and prints out the keyboard events it detects to the kernel ring buffer. We'll check the buffer and see what events are detected. If we see a function key press event, then we'll just write some code to swap the keys and use our custom driver in lieu of the existing drivers the operating system has chosen to interface with our keyboard. To do this, we need to understand the keyboard protocol. So we can actually listen for the specific interrupt generated by the keyboard. We can find the existing protocol by examining the driver the kernel has already loaded. And it looks like in this case, the kernel has loaded the i8042 driver. It's pretty interesting, though it's not totally surprising. It means the kernel has loaded a driver which controls PS2 keyboards. So our little Dell laptop is using this ancient 1980s PS2 protocol for the internal keyboard. You can see this is in contrast to the USB driver that's loaded if we plug in a USB keyboard. Now that we know what protocol our keyboard is using to communicate, we write our kernel module, intercept those calls, and then we're going to print them directly to the ring buffer. After loading our kernel module, we see that when we press the A key, we output all the data to the ring buffer, which is exactly what we expect with the PS2 protocol data. And when we press the function key, again, nothing is happening, which is pretty frustrating, I'm not going to lie. Remember, we're only listening for the interrupt signals produced by the keyboard in this particular case. This means we're literally watching for a change in voltage corresponding to a keyboard press event, and then immediately dumping the information we receive to the ring buffer. So if we don't see anything, this must mean the keyboard isn't even sending the information to our CPU. So I think at this point, we could say we've proven that this is a hardware key. And what I mean by that is it lives in the hardware layer. So is there a way for us to remap it at all? Well, We aren't done. I think there's still a little bit more we can do to try to figure out whether or not it's possible to remap, and if so, how we might do it. So before messing around with chipsec and decompiling the UEFI, I just want to jump to the last layer of the puzzle, just to prevent us from turning up blanks at every step. We might as well just build from the bottom up, since the top-down approach hasn't really worked out so well. The first thing I did was rip open my laptop, a little bit in frustration, hoping the answer would be incredibly obvious, but unfortunately not so much. It looks like the keyboard cable is actually routed through this small I/O junction board, which has what looks like a chip of some sort. The signal is then routed to the motherboard via this flexible flat printed cable. So what's going on with that chip? Are there any other chips on the control path that might also be processing the signal? After poking around, I arrived at this schematic for the XPS 139300, which I think is pretty identical to my XPS 9310. I also found one with a little more detail for this XPS 15 from 2018, which probably isn't that similar, but also not that different. It might reveal something, and it can't hurt to poke around. Looking at this schematic, it seems that there are at least two different circuits that our keyboard signal hits before arriving at our CPU. The first circuit is contained on this I/O junction board, and it seems it goes through this ECE 1117 chip. The second circuit, which is present on the XPS 9310 high-level schematic, is this MEC 5106D circuit. On the older Dell XPS 15 schematic, it seems the circuit is MEC 5105, but I would bet that they're pretty much the same. Also, what's pretty interesting is that we see this thing called BC bus on the schematic. I'm not sure what that is right now, but we're going to keep exploring. Looking at our I/O junction board, it seems that the circuit we need to explore now is this ECE 1117 chip, which is made by SMSC. Rather than poke my machine directly, since I still want the laptop to function when I'm done with it, I thought it would be better to try and explore the circuit using another board. Some browsing online led me to a seller willing to send me some ECE 1117 chips. Some more poking around also revealed a public datasheet for this SMSC ECE 1117 chip. It's probably what the BC bus stands for in this schematic, and so I think so far everything is lining up. While I could try and recreate the circuit from this I/O junction board, there's a couple of problems. First, I don't really want to poke around with any tools unless I have no other choice in case I damage the laptop. Second, if I don't use any tools, the presence of the vias and the lamination choice make it very difficult to visibly recreate the circuit, and there's no way I can determine these SMT components by sight alone. So before I turned this into a $1,000 paperweight, I tried to find anyone selling these I/O junction boards from older models. I wasn't able to find this exact junction board at first, but I was able to find an older model's junction board which has the same ECE 1117 chip and the general components appear similar. So I ordered it along with a keyboard from the XPS 13 2-in-1 model, which has a slightly different connector and worried me a little bit, but it's otherwise branded by the same vendor. Now that I have this chip in hand, I tried to reverse engineer the circuit with some basic analysis and just a $20 multimeter. Using the datasheet for the appropriate pinout diagram, I quickly sketched out the circuit. I attached a breakout board for the 0.5mm pitch FPC and verified everything was where I thought it should be. After reading the ECE 1117 datasheet, it looks like this chip helps control a few peripheral devices, including the keyboard. It takes some inputs and outputs and communicates with the host controller over one of two different protocols. It's either SM bus or BC link. Unfortunately, BC link is proprietary, and I don't want to reverse engineer the protocol since we're already crazy deep into this rabbit hole. Luckily, the ECE 1117 will also communicate over SM bus, which is basically I2C with some extra stuff. At this point, if you have no idea what I'm talking about, the quick overview is that our keyboard is going to somehow send some signals to the ECE 1117 chip, and then the ECE 1117 chip is going to send those signals to some host device, like our computer. The host device might actually be the as-of-yet mysterious MEC 5106D chip, but we don't really know at the moment. For our test, we're going to need to program a host device. I have this small ESP32 development board just sitting here, and since it's smaller than this STM32 and it fits on my breadboard, we're just going to use it. The idea is to program this microcontroller to interact with the ECE 1117 chip, and then eventually view the signals that it's sending when the keyboard is pressed. If we can't see any signal when the function key is pressed, then we definitely know that there is no way to remap the signal anywhere in software or in any circuit above the keyboard, including any UEFI mappings. Reading the datasheet, it looks like the ECE1117 will automatically detect the protocol we're using by examining the data line on the initial falling edge of the clock, and if it's low, which it naturally is in the SM bus protocol, then it's going to use SM bus. After this initial auto detect, we can set the configuration in the upstream bus control register along with this ARA bit, which helped assert ARA functionality, enabling the ECE1117 to send an interrupt command on the SMB interrupt up pin. We should be able to intercept that command on our microcontroller and then do something with it. At this point, we're dealing with electrons more than software, so let's also break out our oscilloscope to get a very granular idea of what we're working with. So wiring up our I/O junction board with the appropriate ground voltage data clock and interrupt pins, we're ready to see whether anything is happening. Flashing our microcontroller with a basic SM bus command to read the control register, we can see that something is actually happening. And at this point, we're also going to break out a logic analyzer to help us better visualize the digital data that's being sent by the protocol. Here, we see that the ECE1117 is responding properly, and we're reading some information off the chip and writing it to our screen. So the next question we should ask is, how on earth does this keyboard pass along information about which key is being pressed? The answer is that it uses a matrix scanning algorithm, and how exactly this algorithm works and understanding the algorithm is a little bit, I think, beyond what I want to get into. But for the curious, effectively the algorithm is trying to solve a resource problem where we have n number of switches, but only p less than n control pins. Since the ECE1117 only has 48 pins, and of those pins only about 28 GPIO-like pins, there's no way to hook up every key on the keyboard to one pin. So the matrix scanning algorithm solves this by organizing the keyboard into a grid, and whenever the keyboard is pressed, one of the low inputs is pulled high, which might be the rows, and then we can scan each column, testing whether we can pull that column high. If we can, then we know which column and which row has been depressed, telling us which key was selected. It's not a much more complicated algorithm, but there are a number of edge cases that we need to consider. So before we actually do anything, let's just see if we can probe the keyboard output and inputs and see if a signal generated on a key press event works. It looks like the function key does generate a signal, which is good news. It means that the keyboard is generating an event, but it's also bad news, since it means that we are likely transforming that signal further up the control path, probably in the MEC5106D chip. The criticality of the MEC5106D chip also seems to be affirmed if we reverse engineer our UEFI modules. We find that this MEC module, which is undoubtedly related to this chip, has some software that appears to set a few configuration options related to our keyboard. The configuration options themselves are probably loaded out of NVRAM, and we can test that when we alter NVRAM directly, the configuration options change in a way that we would expect based on this reverse engineered module. So unfortunately, the MEC5106 is a ball soldered chip, and I don't have the proper tools to desolder, reprogram, and then resolder the chip without likely damaging my laptop. I also can't seem to find a better way to alter the behavior by tweaking NVRAM directly, and based on the UEFI module, there isn't a path to actually alter the behavior of these keys. So it's most likely the case that I would need to reverse engineer the MEC5106D software and then reflash it with my altered software, which itself is quite a project. Hopefully you enjoyed the journey into this kind of crazy endeavor. If not, I'm not totally sure why you're still watching.